All right, everyone. Welcome to the very last class, finally, of this course. So, as promised, we'll cover today generative adversarial networks. And this is one of the most exciting topics in deep learning right now. And the objective function, the loss function that is optimized in generative adversarial networks are usually called GANs for short. Is a loss that we have already discussed in this class, which is the minimum of the max. Remember that? It's a two-player loss where you have two players. One is trying to deceive the other, right? And we, in GANs in particular, we have two players. One is called the generator, and the other one is called the discriminator. And what the goal is the generator is going to be implemented as a deep, usually as a deep convolutional neural network, all right? And it's going to start with an input in some latent space, like in factor analysis and all these other things that we've seen. And from that latent space vector or space is going to generate new observations, right? So from that latent space Z, we're going to generate X's, right? Our inputs X's. And then the discriminator is going to take that input X that comes from the generated or a true input X that I have, right? And its task is going to be to determine whether that input that I've given it comes from the generator, and therefore it's not a true input, it's a generated, a fake input, or it's one of the true inputs, right? The true samples. And to do that, we've seen this, that we can describe this as the expectation of, say, X drawn from Px of the log of the X plus the expectation of Z drawn from some underlying distribution PZ, of the log of 1 minus the discriminator of the generator of Z. Okay. So note what's going on here. This is the loss function, the component of the loss function of the discriminator right here. Right? And remember, I want to maximize this, right? I want the discriminator to learn to discriminate correctly. And here, what I'm doing is I'm computing the discrimination of the images or sample vectors in general generated by the generator network, okay? Now, obviously, this is 1 minus this, because in that case, right, I want to maximize this factor the same way that I want to maximize this, right? So in here, right, this, if I were to maximize this, right, then the generator would win, right? But I want the discriminator to know that this should be a different class, right? A fake generator. So I want the generator to detect this, so I can do 1 minus the output, and for the true ones, just the output itself, right? You see how this works? Yeah.
The output is 0 or 1.
Well, the output can be any number, right? But remember that we have it depends on which network you use, but in general, in deep convolutional neural networks, you're going to have that function h that I talked about, right? That you're going to use. That's going to take the output of the network, right? So this is the output of the network. And it's going to be a mapping function to say, so actually let me say that's in -1 and 1, or 0, 1, or whatever you want to use for that, right? But you have to add this mapping function. The network itself is going to be working generally, not always, but generally it's going to work with real numbers. And then you have to use that mapping function that I introduced. Okay? So the goal of the discriminator obviously is to maximize this, right? To maximize the output of the true and minimize, right, 1 minus the output of the fake, right? And the goal of the generator is the opposite, right? The generator wants to minimize this, right, instead of maximize it. Okay. All right. You may also see this written as follows, and obviously it's the same thing. You may see this as the expectation of, say, x in the space capital X, right? That special notation or font for x that represents the space of the input. And same here, right? You'd have z in my z space, right? You'll see both notations in the literature. Okay, so what's our goal? Our goal is to intrinsically, remember that's discussing in our last lecture, we want to intrinsically estimate this distribution, right? So we wish to intrinsically estimate the underlying distribution PZ, right? Because if I could estimate that underlying distribution, then I can generate as many samples as I want, right, from it. That's my goal. So this is, you may remember when we discussed this topic before, this is called the Minimax problem. And generally use a two-step approach, much like we used in the EM expectation maximization algorithm, right? So what we're going to do, what we could do is we can fix G and perform gradient descent with respect to our loss function L here to optimize the parameters for the discriminator. And once we are done, we can fix D and then perform gradient descent on the function of the, or the parameters, right, of the generator, right? And we can alternate that. If we use base, so going back to our basics, using base, we can write that the optimal classifier, and by optimal I mean base, of course, it's going to be given by px of x over px of x plus p of what the generator gives me, right? The distribution of the, this should be ideally pz, but obviously it's whatever the generator can generate right now, of x, right? Okay, any questions? So while the optimal, the base optimal discriminator is given by base, the famous base equation we've been using throughout the course. A good option for the discriminator is to use a metric that measures the difference between the estimated distribution and the true underlying distribution, right? These are called divergence metrics, as you may know from statistics and signal processing. So for example, one could use the Jason-Shannon divergence. All right. And we can use this as a metric to determine how similar the distributions are. And this would be given by GZ. So this is the divergence between the PX distribution and what I'm generating. It's going to be given by the KL divergence, which is P of X, given PX plus PGZ over my variable Z plus the KL divergence of P of GZ PX plus PGXZ rather. It's my latent space over Z. Right? Now remember that the KL divergence, or Kullback-Leibler divergence, here is, and you know that for sure for signal processing, right? This is nothing else than the expectation over my distribution of the input data, Px, of the log of Px of x over Pgz of x. Correct? So people very recently, in a paper in 2017, so just last year, have shown that if you have a discriminator D with capacity, say n, okay? Remember the capacity of the generator, of a classifier, right, that we discussed in some detail in one of our lectures. Then the generator only needs to remember or I could say to memorize if you prefer, C times n over epsilon square times log of n samples to be able to what's called be epsilon accurate. And that's with regard to, with respect to your loss function, obviously, right? That we have. Okay, and by, don't worry too much about this terminology, epsilon accurate, but it just means that it gets really good, right? That it gets very close to being correct. And the implication of this result is that in practice, the network will not learn to generalize, but rather will learn to memorize these training samples. And what that means, in general, is that GANs do not converge. Do not generally or usually converge. Okay. So it's very difficult to train GANs because it seems that you're not making real progress because of the capacity of the discriminator. So how are you going to solve this problem? And I'll talk quite a bit about this today. Okay. So what happens is that because of this fact, right, that the generator will only memorize this number of samples, right? And at that point, it will pretty much, we can say that, at this point, we could say that the generator saturates, right? To use terminology we've already used. So the generator will saturate. And to address this problem, people are looking into a variety of new loss functions. And I'm going to list several of them that people are trying, or several architectures that use different loss functions. So one of them is called EB-GAN. Another one is called LS-GAN. Another one is called W-GAN. Another one is called B-GAN. Oh, yeah, B-GAN. Sorry. And I-GAN, etc. The list goes on and on and on. There are also architectures that use surrogate functions, optimization functions, or loss functions, such as, let's see, unrolled GANs is one of them. The W-GAN that you have there, hyphen GP, it's another one that uses surrogate. DR, A-GAN, it's another one, and so on. I'm not going to, I don't have time to describe all of them here in this just final lecture, but be aware that there are all these different alternative implementations of GANs right now that people are exploring. And this just happened in the last couple of years, right? Maybe less. So these are things that people are exploring as alternative objectives that sometimes facilitate convergence, right, of the loss function and facilitate, therefore, learning. So another solution, or trick rather, I should say, a trick that people use, is to add weights that are smaller than 1 in the discriminator, right? So what am I? Here. So I could start with the discriminator, I could assign some of the weights in that discriminator to make them smaller than 1, right? Make them really small. So basically, make the task of the discriminator really difficult, at least early on, right? So that the generator has enough time to actually learn to trick the discriminator for a while, because otherwise the generator just gets stuck. Let's see, what else? So in that case, what you will do is you could add this here. You could add, say, one way to do this is to add a W here as well, right? Multiply this by this, and then maybe make this value between, I don't know, 0.8 to 0.9 would be fine, or maybe even 0.7 to 0.9, and then change this over time. so that it gets easier. Another thing that you could do is you could have this Wwait here, if you decide to do it this way, as equal to a function of how well the generator is doing, right? So the better the generator does, then the higher that weight becomes, right? So you can play with these things. Obviously, as always, make sure that when you work with GANs, I cannot emphasize this enough, make sure that your data is normalized between -1 and 1, for example, because otherwise it's going to be really hard to train these things. So you can have also the standard deviation of your data to be within the square root of 2, or a number like this that maintains a certain number of accuracy in your floating point representation, right? That will let your algorithms run smoothly in your computers and your GPUs. Typically in GANs, people in the last layer of these deep convolutional neural networks that people use to represent the generator and the discriminator, people tend to use the 10H function. Remember 10H? And it seems that it is easier to train GANs when you use 10H than when you use other functions, activation functions. So that tends to be a preferred function to use for GANs. Now, if you use Minibatch for training, each Minibatch should include only real or only fake samples. So remember, you have your training set that is now composed of true samples and the generated samples. So if you use batch, right, if you could use all of them at the same time, then you're fine. But if you want to use Minibatch, it's recommended that at each Minibatch only has either true samples or generated fake samples. And that also facilitates training. People find less sparse functions like liquid ReLU to work better than sparse ones like ReLU. So if you want to use 10H is the preferred, but if you want to use other ones like liquid ReLU is probably much better than ReLU. Some other people say that labeling samples in a continuous interval instead of just fake and true, right? So labeling them between 0 and 1 as a real number, that actually works better than just having fake equals 0 and true equal 1 or vice versa. So this means that you need to add noise to your labels. So we could probably represent this like, let's see, we could say that I have my label right here, and then I'm going to add a noise term, right, to my label with, let's say that my noise is between, how about 0 and 0.3 maybe, 0.2, 0.3. I usually recommend that you use ADAM as the optimization algorithm. Remember that we talked quite a bit about this for deep neural networks, but specifically for GANs, ADAM seems to be working better. Now, some people swear by this, that you should train the generator, G, using ADAM, but you should train the discriminator using SGD. So use ADAM to train the generator and use SGD to train the discriminator. And some people say that that actually works even better, right? Yeah, I know. This is so new that we're still not sure what really works, right? So that all I can give you is what people are saying that works for them when they practice this or when they use these algorithms, rather. All right. Now, another way to solve some of these problems that I've talked about here is to use different loss functions, right, other than the minimax. So let me mention some of them that people are working with as we speak, literally. I mean, these are things that are happening right now, people. So this is the most exciting thing in the sense, or topic in the sense that this is still happening in research, right? I can only give you what the latest is, but in a couple of years, I'm sure this lecture will be very different. So alternative loss functions that people are working with and seem to work really well, some of them at least, include the least squares GAN, so LS GAN that I have written down over there at the very end, which does the following. It's the minimum for the discriminator of the expected value of x drawn from the underlying distribution of my density of x, right, of dx minus 1 squared, right, hence the least squares, right, plus the expected value of z drawn from the distribution of z, z the latent space as always, right, and x the inputs as always, of dg of z squared, right? So this is just basic least squares applied to the discriminator or the simples that the discriminator classifies that are either true or generated by the generator. And then minimize for the generator the expected value of z drawn also from my underlying distribution of dgz, right? And now I have this, remember, it's the same as this, but the discriminator wants to minimize this term, and the generator wants to maximize it. So what I'm going to do, I'm going to subtract 1 from here, and that's the same as minimizing, right? So when you work with the minimax, it can be shown that you're actually maximizing the Jensen-Shannon divergence, okay? That's what that corresponds to. This, because it's least squares, maximizes, anyone knows what the least squares maximizes? Chi-square, right? So actually maximizes chi-square, the famous chi-square distance, okay? So there's likely different results, but the authors of this obviously claim that this works better. I think it really depends, honestly. I'm not super convinced, right? I mean, yeah, it works for some problems, but I think at this point, the most important thing is that you know these different loss functions that you can use, and if one doesn't work, try the other, right? Because what doesn't work in one problem works on another. So now another one that people really like these days, it's the Wasserstein loss. So this corresponds to the WGAN that I have here as well. So I've covered this one, and now I'm going to do this one very briefly. And here I want to maximize for the discriminator the expected the expectation, of dx minus the expectation for the latent space of, or variable rather, of the discriminator of the generated functions, right? So I want to maximize this and minimize this. That's what this means, right? And then I want to maximize the generator, the expected value of z pz of dgz, right? Meaning that the goal of the generator is actually to maximize this, but note that the goal of the discriminator is to actually minimize this, right? They have opposite goals. And so of these two, this is the one most people use these days. Okay? So people tend to use either the original loss or this one, right? But try this one if neither of these two work. Now, another extension of GANs that's very useful, that's an extension of GANs. You can use whichever of these different loss functions that I've described, these three different losses, or some of these other ones that are given in these other architectures or methods. So once you've decided which of these loss functions you're going to use, you may also want to work with what's called conditional GANs. And this is the same as conditional probabilities, right? I want now to estimate the probability x, whatever, p of whatever, right? Condition to some observation, right? To some fact that's known to me. So in the original GANs, maybe let me do that first. In the original GANs, what I have to give you an illustration of what these things look like, right? In the original GAN, what I'm going to have is the generator here somewhere. So I have this space Z, right? This is the latent space, right? And now here I have my samples, right? Z1 through Z, I don't know, M, right? And I have actually, I'm completely wrong. This is totally the opposite, isn't it? This goes from a latent space to an input X. So that is the decoder that we saw yesterday. So you get one of these ZIs, right? And ZI is represented in some latent space of, say, Q dimensions, right? And now this is going to give you the corresponding outputs. So why don't I call them maybe X1 prime through XM prime, right? So these are the outputs of the generator, right? So this is my generator network. Okay, so far so good? Okay, now I also have my original sample vectors, right? X1 through maybe XK, right? These are the true simple vectors that I have. And now I'm going to use this vectors and the true vectors and the fake generated vectors. And I'm going to input them to a discriminator, right? Network that is going to output a real or fake output here. So this will be my classifier, right? Okay. So in conditional GANs, what we're going to have is exactly the same architecture that I have drawn here, but I'm going to add a condition. So now I'm going to have, actually, why don't I just do that right there? It'll be easier. OK. So what I'm going to do now, I'm going to add, say, variable y, right? In some space, say capital Y instead of Y. I don't know. I know how to do capital Y. All right. I'll just do simple Y. All right. So in the space of capital Y's, this is just my samples of conditions. So I may have Y1 through YP or R. And I'm going to add this first to the generator, so I can condition what this generator does, right? And then I'm going to also give that information to the discriminator, right? To tell the discriminator what am I trying to do right now, right? What am I conditioned to? Make sense? So if you go to the original Minimax problem, you can write this down as the minimax of the expected value of the log of d of x now given y, right? So this is my conditional probability right here, right? Plus the expected value of z of the log of 1 minus the discriminator of the generator of z, given y. There we go, right? Which is the exact same loss that I've defined earlier, but with a conditioned, right? Conditioned with that variable y. Now, this is for the original loss that I introduced, but you could do that with any other loss that I have mentioned as well, right? All right, how are we doing on time? Because it's going to be a tight one. All right, I'm going to jump ahead, a little ahead. So I want to make sure that we have enough time to cover the basic concepts at least. So with GANs, you can also train a system to learn a joint distribution, right? So it'll be training for joint distributions. So we've seen how to do conditionals. Now let's see how we can do joint distributions. And to clarify, so here I have the probability of, say, x1, x1 all the way to, so x1, x2, all the way to, say, xr, okay? And so, for example, let's see, an example could be x1, x1 may be a binary, right? A binary variable that specifies, let's go to computer vision, because most of this research is in computer vision. So in computer vision, for example, you take an image, right? This is your image. And your variable x1 may specify whether that image was taken during winter time or summertime, for example, right? So that could be 0, 1 or negative 1, 1, or representing winter and summer, right? x2 could be maybe whether the picture is of, if it's a person, let's say that it's a face, it's a male or a female, or if it's in a scene, it could be whether it's see, mountains versus, I don't know, a cornfield, right? Whatever you're representing, beach area, right? The ocean, etc., right? And so on. So what we're going to do, we're going to define a tensor. Let's call it x, right? That combines all my different variables, right? x1, x2, xr, right? Okay, so, and now what you're going to do is you're going to convert everything that we have done here from these vector representations to tensors. That's it, right? It's as simple as that. Now there is a problem. The problem could be that there are unobservable points, right, in some of these variables. So for some samples, this is not observable, and for other samples, this is not observable, and for other samples, this is not observable, right? So how do you solve that problem? And the way people solve this, if this is the case, which is a hack, really, not really a solution, but a hack. So what people will do, will use multiple generators, right? So they'll have, say, my G1 here, generator 1, that comes from my latent space Z, right? And they'll use, say, a generator 2 for the second one. And then they'll combine this here with a function, say, g. Okay? And if you have more functions, then you keep adding networks. So an interesting application of this, for example, is to generate video, right? So imagine that you want to generate instead of images, right? So here, remember, if I'm using computer vision, these ZIs are going to be images, right? Matrices. And I'm going to output matrices. These are matrices, and then, or a vector representing the image, right? If it's vectorized. And then I'm going to output whether this is a true or false. Simple. But how about if I want to generate video, right? So in that case, I could do something like this, where I could, for example, represent the foreground and the background, for example, right? Just to give you an example, right? You may even include something else here, which is another network that is going to determine where the foreground and the background are. So let's say that this is, let's call this, let's see, I'll call this the foreground and this the background. Oops, not GB, right? So let's say that this is the background of the image, this is the foreground, and now this M is going to determine, so it's going to be, so let me do a small m. This M is going to be the product of this times F, right? So what that means is that the element-to-element product, as you know, plus, what is it going to be now? 1 minus M times B, right? And that's going to be my G function. You see how this works? Right, so I have a generator that generates some background, generator that generates some foreground, and then another generator that determines what goes where, right? And that way you can generate images, video, so on, right? All right. People are using this also to learn multiple representations simultaneously. So let's see how we can do that. So in some cases, one may want to consider the output of the network to represent variations of the vectors that we have in our latent space, right? And there is an architecture specifically for GANs that was proposed, was actually just published this year, which is called StarGAN, that will do just that. It's similar to the idea of conditional GANs, in which you have an additional input to the generator. So let's see, if that's my generator here, let's call this G as always, right? I have my input image. Okay, right here, can everyone see? Yeah. So this is my input image. It goes into the generator. It's the same thing as this, right? I haven't done anything different yet. Now there is my target domain, and that is, again, very similar to what I did with conditions, right? With conditional GANs. So I'm going to specify now here the target. I say very similar, it's really the same thing, but it all depends how you call these things. And now this is going to give me my fake sample. And now I'm going to take another generator. Okay, how am I going to do this? Okay, so I'm going to take another network here. I'm going to take this as input. I'm going to take the target domain here, obviously, to know what I'm doing. And I'm going to now try to reconstruct the original input image. Okay, so now I reconstruct the original image, right? Or sample, if you prefer. So I'm going to use a second function that has to be the same. At the end, it's just the same network reapplied, okay? That will generate another image. So let's see how this works. I start with an original image here, right? So imagine that's an image of a face, for example, right? So we have an image of a face right here. Now, I pass it through this network, and I output another image. And let's say that this image that I output has, I don't know, maybe change the gender of the face, right? So if that was a male, now it's a female. If it's a female, now it's a male, what have you. Or maybe this one is smiling and this is frowning, right? Or vice versa, okay? And now the goal is to reuse this to reconstruct that original image right here, okay? Now the thing is, I can specify a target domain. And I can say, okay, change the hairstyle. And it will change the hairstyle and then back to the original image. Or change the hair color and then back to the original image, right? So it's kind of a decoder, the encoder decoder, but I'm not encoding or decoding because the output is the same dimensionality as the input, right? But it's the same idea of the encoder decoder that we saw in our last lecture. So I can change the hairstyle. In another target domain, I could say, okay, change the gender of the person, or change the identity, or change the pose of the face, and so on, right? So I can actually reuse the same architecture to do this multiple times. And the loss function, in that case, is going to be equal to the expected value, as always, of the log of the source. I'm going to say the discriminant of the source, right? The source, the original source that I'm given of x plus the expected value of x comma c, which is my condition because I'm conditioning this. And this is now going to be the log of 1 minus the discriminator src of the generator, right? One more. Okay, where remember this is now the one that defines a distribution over the original space, right? The source space. And then we're going to use, so this is the original so-called sometimes adversarial laws. Adversarial because there is this generator that's trying to create adversarial attacks. Remember the adversarial images that we discussed, right? So it's trying to generate adversarial attacks, the generator. So it's sometimes called the adversarial laws. And now what else do I want? So this takes care of this part, right? You agree? This is what we had defined here, right? There's no difference, right? So this loss has not changed, but now I need to add this second component. And what I'm trying to do, I'm trying to reconstruct the original image given the fake image, right? Or the fake sample. So now I'm going to add a reconstruction loss, let's call it LR, which is the expected of x, px, x prime now, px, of negative the log of dc, c prime given x, okay? Where now dc is the probability distribution over the domain labels computed by the discriminator, okay? So finally, we're going to combine these two losses into a single loss. Let's call it maybe capital D for the discriminator. For the discriminator, I want to minimize, remember, the so-called adversarial loss. And I want to maximize the reconstruction. So I'm going to add the negative sign here, and then this one. And it's typically, obviously, to add maybe some regularize some constant, right, to determine the degree of importance of each of these two sub-losses. Okay, and two sub-losses, I'm sub in quotation marks, because they're part of the same loss. And then for the generator tries to fool the discriminator. So this is going to be positive now because you try to maximize this, plus lambda 1 LC, plus lambda 1 wait a minute. Oh, yeah. Plus lambda 1 plus lambda 2 should be now. There we go. LR. Where now LC, right, this other loss, is the domain classifier, right? Oh, gee. All right. I'm sorry, guys. My bad. This should be the domain classifier, right? Oops. I knew something was wrong. Yeah. Right. This is the domain. So this is how this controls the domain, right? Here, right? The domain given the image, right? Right? And the reconstruction loss has to measure how well I reconstruct the image. And of course, you can use whatever norm you want, right? I'm going to use norm 1, but you could use norm 2. You could use the 0 norm, right? And so on, depending on how you want to measure things. So the expected value is going to be of x minus, what am I looking here? Let's think about this for a second. So I have, this is the original, right? And the reconstruction has to compare the original with this one here, right? Now this one here uses a generator of this fake image, which has to use a generator of x, right? So I'm going to have g of x, right? And given, so this first one is given by this, say, c prime, and this by this c, right? Of the conditioned that I add, correct? So where am I? Here. So I'm going to have g of xc c prime. Am I doing this right? First should be c, right? Because this is the first time. And then second should be c prime. And as I said, you can use whichever norm you want. Typically, people will use a sparse norm, like the 1 norm. But you could use the 2 norm. You could use whichever norm you like. That's more appropriate to your problem. OK? Any questions about this? So let me show you an example application of this. Where's my, oh, here it is. So let me derive an application of this for generating images with different facial expressions, images of faces, that is. So I'm given, this is my problem. I'm given an image of a person, of the face of a person, and I want to edit the expression of that face, OK? And now you may remember that I talked about this in a lecture, that the way you create facial expressions, the way you produce a facial expression, is by moving your facial muscles, right? These facial muscles are called action units, small detail, or AUs for short, right? So I want to now have a network like this, where I condition it here with action units, right? So I can have a vector of action units, right? A vector here that has zeros and ones, specifying which AUs or which facial muscles are active and which are not active, right? Simple as that. And now I have an original image, and now I say the output fake image should have this active and not active facial muscle articulations, right? And then when I want to reconstruct it back, I need to have the action units of this original image, right? And I've already showed you that we already have algorithms that can determine what are the action units of that image automatically. I don't have to tell the system already knows, right? Okay, so we're going to start with a set of images. Let's call it IYR. There are color images. So let's say that they have a height of H, width W, and 3. It's a number of channels. So RGB, for example. And I have my vector YG that specifies the action units that are going to be active. So Y1 through Yn with Yi either 0 or 1. Or it could be a continuous value between 0 and 1 or just 0 ones. The goal, our goal for the network, right, is to, in an unsupervised way, obviously, to find the mapping, let's say M, between this set of images, given this condition right here, into generating another image. Okay, so this is the original image. This is the new generated image corresponding to that vector, right? So this YR specifies the action units that are active in my input image right here. And this YJ, remember, is the action units that I want active in that output image right here, right? Make sense? And let's see. So I want to learn this mapping. And since this is unsupervised, we do not have these images here, right? I have no ways of knowing what this image looks like. Or, well, I do, but the system doesn't, right? So it has no ways to knowing what this is going to look like. So what I'm going to have, we are going to use this architecture to see whether from these fake samples, right, when they are used as inputs to the same generator, I can correctly reconstruct the original action units that I do know, right? These action units I do know. Because I have an algorithm, not because they are given to me, because I have an algorithm that automatically tells me which action units are present. Okay, so I'm going to use that fact to train the system in a completely unsupervised way. All right, so let's see the algorithm. So for the algorithm, we are going to use the generator. That I'm going to condition on YG. And when I get, so if this is my, here, my IYR, and this regenerated image, this reconstructed, is the same with a hat, let's say, as we've done before, right? I want to see that these two are similar, right? So the goal is to have this approximately equal to this, right? This is my goal, correct? All right, so I'm going to use, to determine this, I'm going to use a discriminator to tell me whether the generated image, right, looks good or not. Should be G. All right, I'm going to skip some details because I'm running out of time, as per usual, right? But today it's the last class, so I really have to catch up. So I'm going to post a paper with the details of the loss function. But basically, you have a loss function to generate the image that evaluates the generator, the discriminator of the image, the original image, and the vector of action units. Okay? So I'll leave you to read the paper to see what this looks like. Okay? So I'm going to skip all this ahead. And I'm going to turn to very quickly to some slides. Okay, so let me just show you some examples of these GANs, of how this works. Now this we already covered the other day, so I'm just going to jump ahead. You have in the slides, as always, the equations that we have presented here. This would be a classical deep convolutional neural network that you use for the discriminator and the generator. Usually you just use the same network for both, right? You just simplify things as much as possible, or very close. They're very similar, because you don't want one to be much better than the other, because otherwise these loss functions are not going to converge. So here are things that you can do with these networks. It's really cool. So you can train them to generate smiley faces, right? And we'll just learn to generate the smiley faces like this. You can train them to generate neutral faces, right? But you can also, as I've shown you, you can train them to generate, say, neutral faces, women neutral faces, or men's neutral faces, right? And now, given this image, right? This image corresponds to a latent variable z, right? Or let's say z1. I can subtract this z2, the latent variable of that image, right? Which basically subtracts from this the concept of women, and add the z3 vector that corresponds to male, and I'm getting then a smiley faces of male people, right? Of males, right? So anyways, but let me show you. You can do this with sunglasses and many other things. But this is the one I was trying to finish on the board, but I was unable to give all the details. Again, look at the paper in Canvas. But this top row here, these images are all the exact same image. And this is the original image. And all these ones are images generated by the generator network. And the discriminator can still tell these are fake, but we can't, right? Generator is so good at this point, after you've trained this network, that you can see. So action unit 1 is the inner corner of the eyebrows moving up, right? So you can see that you can do it more or less, right? So it keeps increasing the motion upwards. AU2, it's the outer movement of the brows. You see that? AU4, it's the furrowed brows. And then you can say, OK, this is a true image. This is an image I'm given. This is a real image. And now I can ask the system, OK, add action unit 12 and 25. 12, it's the classical smile. OK? And 25 means mouth open. And the system will generate the sequence. And all these images down here, they're all faked. They're all generated. All these images are a result of the generator. So basically now you can just generate any image that you want. Okay? It's pretty crazy, isn't it? This was just published a few months ago. So in the slide, you have more details about the network, what I said, this star GAN architecture idea. And this is just the same thing applied to different images in the movie format, so you can see what happens. Another application of this that is just happening right now, this is really cool. And these slides are from a good friend of mine that I asked him to send them to me at Rutgers. That you can do the same thing that I've said here, but for art, right? So you take real paintings, right, of some whatever. You can condition that too for, say, you know, impressionist art or abstract art or whatever art, right? But you can train these GAN networks to generate art, and then a discriminator to discriminate whether it's fake or true art, right? And then the networks learn to do things like this, right? That's amazing. So this right here is one of my favorite. This is a painting generated by one of these networks. This is stunning. I mean, I love this painting. I would buy it, wouldn't you? This is absolutely fantastic. All right. So there was one painting that was generated by a GAN. It was also generated by, or with the help, say, of some artists, right? So there was a collaboration of GANs and artists that was put in auction by Christie in New York City recently, just a few weeks ago. And people were wondering why Christie would, you know, which is a very high-end auction house, why would they auction a painting like this? People expected maybe it would sell for $10, $20, maybe even $30,000 or $40,000. It sold for over $400,000. Do you want to make a quick buck? Learn to use GANs. I mean, seriously, right? That's a lot of money. So you have a lot of slides on this. All these are fake art, but I mean fake. I mean, depends what you call fake, right? I mean, to me, this looks like real art. So art, only that it's not done. It's not painted by a professional. It's just done by a machine, right? But who trained the machine? Obviously, we did. So here are some more examples. That's pretty cool. What do you think? I mean, this is pretty neat. So this is all I have to say. This is the last class. So just hope that you enjoyed it. There's a lot of material that we've covered. Oh my gosh, this is 27 lectures, I think, right? Or something like that, 28. And I just want to say that there is a lot still being done in research, obviously, with regard to, in computer vision, with regard to deep learning. This is a plot that I found online on the number of papers in deep learning for the last several CVPRs. There was CVPR in Columbus when we organized CVPR here in Columbus in 2014. That was maybe the very beginning of networks starting to become more popular. But since then, it's exploded. And the most famous for a while were the LSTMs that I talked about a couple lectures back. But now GANs have taken over. GANs are just so popular right now because of all these things that I was discussing, right? I was trying to get to cover. Now, NIPS, NeurIPS, excuse me. NeurIPS, they've changed the name, finally. NeurIPS is the top machine learning conference. And here you have the number of submissions over the years. And you can see the number of submissions in dark has gone from about, I don't know, maybe 200 in 85 to actually, this is probably not that accurate. I think it was more close. I think it was over 4,000 this year. But anyways, this is from last year at NeurIPS. And let's see, does it say? I don't think it says. Well, this is the number of accepted papers. But as you can see, the percentages, so you can get an idea. Oh, here it says, this is the total number of submissions. So I think that this is incorrect. This number is for last year. This year, there were probably closer to 5,000. Now, in CVPR, This is a main computer vision conference. This year, we just had the submission, and we had over 5,000 submissions. Now, when I organized CVPR here in Columbus, we had about 2,000 submissions. That's just 4 years back. We've gone from 2,000 to over 5,000, just slightly over, but over 5,000. That's more than double. It's a 250% increase, which is extraordinary. So there's a lot of interest on this. I want to qualify this. This is a plot of the number of submissions as it's increasing for NeurIPS and CVPR, for example, which are these two right here, computer vision and machine learning. ICML is another machine learning conference. But I want to caution that artificial intelligence conferences were at this level in the 1980s, right? And what happened? That we had one of these so-called AI winters that people were overpromising what they could do. It didn't work out, and interest just dropped so dramatically that these communities have not recovered. Look, as machine learning and computer vision have skyrocketed, these AI conferences have never recovered, right? So you have to be very careful. But there's a lot of excitement in this area. If you want to get to this, right, this is the time. Oh, this is the number of submissions. Now I see. This is the number of submissions for NIPS this year. So I was wrong. It's even over 7,000, right? Huge. So this is the time to be in this area. You're very lucky that this is your time. So work hard. A good thing to do now that you have finished this course is to probably rewatch the lectures. I know it's a tremendous amount of work, but if you could rewatch the lectures, you're going to get so much extra from this class, right? Because now that you're equipped with all this knowledge, reviewing all this material is just going to help you tremendously. But another thing that you should do is go online after you rewatch these lectures. Go online, download papers from the ones I posted in Canvas, the ones that you are interested in online, read these papers. There are tons of other lectures in YouTube, I'm positive, right? There have to be thousands of them. Watch them, right? These conferences, NeurIPS, CVPR, we always post only the talks, obviously. The posters cannot be online in YouTube, but the talks are always available online, right? Watch the ones that you're interested in, because this area is exploding right now, and there's just so much happening. It's going to change your life, okay? Hope you're the best, and I'll see you next year if you stick around.